In our notes today, we're going to be talking about the differences between linear, exponential, and quadratic functions. We model linear situations. We model situations that have a constant rate of change using a linear function. Everyday examples include monthly payments for rent or an hourly wage. In the table below, you'll notice that our x is increasing by 1 every single time, and our y is increasing by 2. This means it is a constant rate of change because it's not changing. It is being consistent. If we wanted to find the slope for this, it would be y over x, which is 2 over 1, or just 2. So that means that this is changing at a rate of 2. We model situations that have an average rate of change using exponential functions. Everyday examples include population growth, radioactive decay, or loan interest. You'll notice in the table below that our x again is increasing by 1 every single time, allowing us to focus on our y. 1/8 to 1/4, 1/2, 1, 2 to 4. This is a multiple of 2. So when it is multiplying or dividing, we think of exponential functions. When it's adding or subtracting, we think of linear functions. So if I were to multiply by 2 every time, that would demonstrate the pattern we see in the y-axis. So if we were to find the average rate of change, which is our b value, it would be 2. Quadratic functions, we model situations that have a constant rate of change in their second difference meaning subtraction using a quadratic function. Everyday examples include the trajectory of a ball, an arrow, or a missile. So quadratics are really good at determining arcs and figuring out how something travels if it's not going along a constant rate of change or a multiple. So you'll notice that in our x, again, it's increasing by 1 each time, which allows us to focus on the y. 9 to 4 went down by 5, 4 to 1 went down by 3, 1 to 0 went down by 1, and then we increased by 1, 3, and 5. Now this is not a constant rate of change, nor is there a multiplication or division pattern. However, if you were to look at the difference between these numbers, you'll notice that it is constant. Between -5 and -3 is 2, -3 to -1 went up 2, -1 to 1 went up 2, 1 to 3 went up 2, and 3 to 5 went up 2. So we are able to identify quadratic functions when we take their second difference, meaning we find the difference of the y values, and then we find the difference of those numbers. And that tells us whether or not it is a quadratic function. If we're looking at equations, linear equations have an x with no exponent. So something like y equals 5 to the x is going to be linear. So let's just make sure with our calculator, 5x plus 1, 1/2 x we graph both of these, and we see that they create straight lines. So as long as there is an x value with no exponent, we know that it is linear. We know that something is quadratic if it has an exponent of 2 for the x value in the equation. So let's graph the first two equations and see if this is true. So that's those first two equations. When we graph them, we notice that it creates a parabola for the first and for the second equation, which is at the very top. So if it comes down to noticing that something's a quadratic, it is because there is a x with an exponent of 2. exponential functions are going to have an x in the exponent. So that means that the variable is in the exponent. This is the only type of function that has that. So if we were to graph these, 3 to the x plus 1, we see that it creates a curved line. If we were to graph the second one, 5 to the 2x, so we've given our exponent a coefficient, which means it's doubling the exponent. This also creates a really curved line that's hard to see, but in both cases, you're going to get a graph that looks flat and is then curved.